We are swimming in numbers and data every single day, right? But what if I told you there's a simple, powerful language hidden inside all of it? Today, we're going to learn how to speak that language to see the stories that numbers are really telling. So, this sounds like the beginning of a weird joke, doesn't it? A cyclist, a medical test, and a pair of dice. What on earth could possibly tie all of those things together?
Well, it turns out they're all just puzzles. Puzzles that become surprisingly easy to solve once you understand the clear, logical language of numbers.
And that's exactly what we're going to do. In just the next few minutes, we're going to pick up the fundamentals of that language, giving you a powerful new tool for thinking critically about, well, pretty much everything. Okay, let's dive right in with a real-world example. We've got a bunch of power output data from 14 different cyclists. The big question is, how do you boil all of that down to just one single number that tells the story of the whole group's performance? To find the center of our data, we've got two main tools in our toolbox. First, there's the mean, the classic average we all learned in school. The only catch is it's a bit sensitive. One really high or low number can throw the whole thing off. And then you've got the median. The median is just the rock-solid value in the dead center of the list. It couldn't care less about the extreme values. For our cyclists, if you do the old school math, add them all up, divide by 14, you get a mean of about 192.57. Seems simple enough. But if we line up all those numbers from smallest to largest and find the exact middle point, we get a median of 189. Pretty close, yeah, but a different story is about to unfold. So as we're scanning the data, one number just leaps off the page, 244. That's way higher than everyone else. We call that an outlier. So what if it was just a typo? How does that one little change affect our entire summary? Let's change that 244 to a more typical value, say 204. And boom, look at that. The mean immediately takes a nosedive, dropping from over 192 down to 189.71. That one high number was really pulling the average up, wasn't it? And this is where the median just shines. Even after we changed that outlier, the middle value in our list doesn't move at all. The median stays exactly the same at 189. It's totally unfazed. And here's the key takeaway. When your data has some wild extremes, think about house prices in a neighborhood with one giant mansion. The median is often going to paint a much more honest picture of what's typical than the mean. So we've seen how to find the story in data that's already out there. Now, let's use numbers to peer into the future and actually calculate the odds of what might happen next. We'll start with the classic, rolling two dice. This simple grid lays out every single one of the 36 possible combinations you can get. This is our entire universe of outcomes. So, what's the probability of rolling a total of 8? We just look at our grid, count up the number of ways you can get an 8, yep, there are 5 of them, and put that over the total of 36 possibilities. Simple as that. Now, let's apply that same logic to a real-world scenario. A real estate agent needs to get into a house. When you really think about it, there are only two ways this can happen. Either the house is already unlocked, or it's locked and they happen to have the right key. To solve this, we add the probability of the first path, that 40% chance it's unlocked, to the probability of the second path. For that second one, we multiply the chance it's locked by the chance they have the right key. Put it all together, and they have a 62.5% chance of getting inside. All right, buckle up, because this next section is where probability gets really interesting and can seriously mess with our intuition. We're going to look at a medical test that seems totally straightforward. Here's the scenario. A disease affects 7% of the population. There's a test for it that's 95% accurate for healthy people, but it has a 10% false negative rate for people who are sick. So you get a negative result. You should be completely relieved, right? Your chance of being sick must be tiny. Well, let's run the numbers and see. First, let's find that small group of people who actually have the disease but get a false negative result. That's 7% of the population times the 10% error rate, which gives us a tiny 0.7%. Okay, now let's look at the much larger group, healthy people who get a correct negative result. That's the 93% of people without the disease times the test's 95% accuracy for them. That gives us about 88.35%. Now, let's add those two groups together. The sick people who tested negative and the healthy people who tested negative. This gives us the total group of people who get a negative result, which is about 89% of everyone who gets tested.
And here is the mind-bending conclusion. To find the odds you're sick given that you tested negative, we take that tiny 0.7% group and see what slice they are of all the negative tests. The result is shocking. There's still a nearly 0.8% chance you have the disease. It's small, sure, but it is not zero. Our intuition was completely wrong.
For our final topic, let's shift gears a little. We're moving from calculating chance to simply counting possibilities, especially when the order of those possibilities makes a huge difference. The fancy mathematical term for this is a permutation, but all it really is a way of counting arrangements where the order is key. Think about it. Electing a president and a treasurer, who gets which job, creates a very different outcome.
So if a student club has 50 members, how many ways can they pick a president and treasurer? Well, there are 50 choices for president. Once that person is chosen, there are 49 people left for treasurer. You multiply them together, and you get 2,450 possible leadership pairs.
This gets way more interesting when we add a condition. What if two friends, B and C, will only serve if they're together? We solve this by splitting it into two separate scenarios. First, the case where they do serve together, that's two possibilities. Second, the case where neither of them serves, where we just choose from the remaining 48 people. We calculate the number of ways for each case, add them together, and that gives us our new total. We've looked at describing data, calculating odds, and counting arrangements. After all of that, what is the single most important takeaway from learning to think with numbers? It's this: learning statistics isn't really about finding the right answer. It's about learning to ask the right questions. Questions like, should I be using the mean or the median here? Or have I considered all the possibilities? And what hidden assumption is tricking my intuition? Asking those questions, that is the real power of speaking the language of numbers.